So let's start. Last time we discussed this Windman cutting rules, which was a test for unitary. So this was one way of writing basically this. Now, in this equation, actually, we wrote it in terms of these diagrams, where you can see just these are my usual DF and DF star kind of propagators will come in here, which are time ordered and anti-time ordered. In this hand, on the right hand side, in terms of the diagrams, we have this so one circled and one uncircled kind of thing, where delta plus and delta minus contributes. And in those cases, we basically describe that in a picture of this kind. This delta plus and delta minus are correspond to this summing and identifying the legs of these two pictures and summing over all of them. So these pictures basically have to do with this sum over n external states here. And so now in this, while talking about these things, we also saw that we had to deal with time ordered, anti-time ordered, and no time ordering propagators, which is also the case we saw before in finger-English formalism, that we have different kind of cases where we might have different operators that different kind of time ordering that might be there. So here it was time ordered, here it was anti-time ordered, and this was for time ordering basically, which correspond to this delta plus and delta minus. And we also these two are function. We also saw that let's say this is GRR, then GRR plus GR. So now what we can do is we can identify this kind of thing to BF, this to BF star, this to delta plus, this to delta minus, and also the case, an important point is that in finger-English we had in fact two kind of fields. Corresponding to the upper branch and the lower branch of this finger-English contour. So now what we do is we can go to a new basis which is called the average difference basis, where we define certain average fields and difference fields. What happens is basically instead of four such Green's functions, in this basis we actually get three coordinators, and fourth one goes to 0. How does that happen? Is basically the first one we get is say this time. These are nothing but again GRR, GRL, GLL, GLR, and we know that GRR plus GLA is equals to GRL plus GLR. So in fact we can write this as either of this way, either in this way. We have to change this 4 to 2 or this way. So first term of each case is Q1, second one is Q2. This is typically called on this basis Green's function. Then we can have a mixed kind of mix. It will just be, you can work out. This one can directly this is in terms of original fields where we had still no phi r, phi l. So because this and this equals to this plus this. This comes from this point. This has to do with this theta function for the wings. In one case, T1 has to be greater than T2, and in this case, T2 has to be greater than T1. The final thing, which is the phi t phi t equilibrium. This will, in fact, we will be able to show that this will be phi r phi r plus phi l phi l. Now using the again similar motion, this is GRR, GL, GRL, GL. So this in fact will be 0 because there is minus signs with these two, and in the propagator level, we can understand in this average difference basis, phi d, the difference correlator becoming 0 as the cutting equation or the largest line equation, that is that equation I plus I star. Maybe one would think that since this was a test of unitarity, this being 0 might tell me that my query is unitary, which is definitely the case. But then you would expect that in a non-unitary theory or in a non-unitary Schiller-Keldysh formalism, you will get this phi-d correlator, difference correlator to be non-zero as a measure of non-unitary. But we will see whether that happens or not. So how we are not completely sure yet how to see the effects of non-unitarity in a, let's say, perturbative treatment where this Wettman rules were valid. So to do so, what we will study an example today, which is the phi-4 open quantum field theory. And we will see some actually surprising facts which might not be clear except we do computations or except we study the example. So we already know that open quantum field theories are effectively they are effective field theories that are very different from usual theories in the sense that they are non-unitary. There we have this in the Schiller-Keldysh action. We have a influence functional. You have to include the cut diagrams in the possible Feynman diagrams as well. Where in this equation it was not the case. The original diagram was always a usual diagram, and this was all circle diagram. On this side we had this identity which included this some uncircled, some circled, which sort of took care of these cut diagrams. But in the future, in general, have cut diagrams and Feynman diagrams as well in the perturbative expansion. And so, in open quantum field theories, the light fields are typically integrated out, not the middle fields, in the sense that, for example, in studying the quantum Brownian motion, one integrates out the light water molecules and studies a heavy particle going through that water molecule and studies basically the motion of that heavy particle. So we know that in our usual Schiller-Keldysh for a unitary case would write this like this action, and in a non-unitary case we will also have a influence functional which is a mixed field term. So what we will do is taking this input into consideration, we will try to write most general action that is local and non-unitary. So we'll try to write some mixed field terms as well. We should mention that there is no specific reason to consider the local part here. We could have also taken some non-local fields in mind in our Schiller-Keldysh action when we try to write it down. But very less is known about quantum field theories in general. So we'll start with something which is still local in the fields. So phi-4 theory equals to 4. Z is a coupling. can already see that I have already included one mixed term here. I also have for phi r fields, I have to change the sign here. This will be Z star. Plus imaginary part as well. We have sort of written all possible local and non-unitary terms as well, and so what we will do is basically all of these are couplings for now, and in fact they can be the Z in square. These terms can also be in general complex couplings. And the cross couplings are which couples phi r field to phi f field. So these are cross couplings. Sigma Z delta square delta and lambda. So our idea will be to study this theory or this action as a deformation from a unitary version of this action where there was no mixed terms and also no complex parts here. So my sort of my unitary version of this theory, so we treat this as a deformation, perturbation in terms of the perturbative constants, that perturbative coupling that we will get. Unitary action will be given back. So the way to go to unitary theory is to turn off the cross couplings as well as the imaginary couplings. So we will only take the real part of these couplings, and then that will be our unitary theory. So the way to write that is phi unitary. That is basically just d4x half of d of z. Plus same things, same things, what only do 5 square, square. This is just to consider the most general term you should also consider in this kind of terms, complex part. This will not be in the unitary theory because of course in general my influence function is supposed to be complex because I'm treating it to be non-united. Sorry? No, here we have already considered I inside this. These couplings we will treat as real couplings, and I am putting an I in front of the this kind of mixed term. This is not very. I don't think this is very important going forward. So this you can choose in different ways. You can choose this to be complex and then yeah. Not only this term comes off, but you also see that there was a mixed term. So sigmas go to 0 as well, and these were in fact I mentioned that in the most general situation I am considering these to be complex. So for real couplings I will also turn off the imaginary part of these couplings, Z, int square and lambda. So in fact when I now think from going from this unitary theory to that non-unitary theory, my couplings will be actually the full list of couplings will be this one. Then the cross couplings. And but we can see that now if you remember this previous version of this kind of thing, and here what we consider the, let's say my is phi r will be just this part, right? Real of these parts. Is phi r and is phi a. Rest of all the things that we have from here, they are all mixed terms. So basically, if you remember, I wrote down the influence function in a unified form, and it was written in this way. Considering more general term than what I wrote earlier. I probably wrote earlier just L alpha, diagonal alpha, but we can consider more general kind of terms in our action. Now what I would like to do is basically there are all these parts. So my unitary action is of this one unitary action, and you can think of this as this phi r minus s phi l part. So in my influence functional there will be the imaginary z multiplied by delta phi r square, imaginary z star multiplied by del phi n square, and so on. So those terms will contribute to pure phi n terms in the linear motion. There will be just phi r terms will contribute to, for example, one of these example will be imaginary of z del phi r square. This will also come in here in this way. Then we'll have half of imaginary n square into phi r square. This term will also come in here. Now here the operators are this L alphas and L beta we can relate to this del phi r or phi r square. But what we want to focus on is these couplings that were present here again. And see that this Liebman operator was written in such a way that the couplings for the alpha beta term in pure phi r contribution or pure phi l contribution is equal to the Lindblad part of the influence function part of the mixed phi r phi l contribution. For example, in the mixed phi r phi l contribution, what do we have? We have this z delta. Let's say for this case that when we are taking imaginary of z and my L alpha phi r or L alpha phi l is basically del mu phi r or phi l. Then in the mixed term, what will I have? Del mu phi r, del mu phi l. Here, what do I have with that term? Z delta. So I will be able to get some conditions from this kind of this coupling being same for this kind of terms, which are called Lindblad conditions. For example, the imaginary of z has to be z delta. Imaginary of m square has to be m square delta. Imaginary of lambda plus 2 imaginary of sigma. This is a little involved. After you deal with this kind of operators that I gave an example of, this kind of L alphas will give rise to this equation. M square equation will come from phi r kind of consideration. So if you just consider L alpha to be phi r, then you will get this equation. And rest of the things, that is this phi r to the power 4, phi l to the power 4, or say all of these terms like phi r square, phi l square, whichever multiplied to some phi field going to the power 4 action, that part if you will get, then you will get this third Lindblad condition. And this basically ensures what, if you see that what the way we are going through or we are deriving these conditions is by saying that what was my unitary action, what was added to the unitary action to make it non-unitary. So it always from that action coming from this action to this equation, you can think of this line being in middle so that we can associate different other parts that are not in this action to each other through this equation, which is imaginary of z going to z lambda and so on. So in this process, we are basically this Lindblad conditions. They ensure microscopic unitarity of system plus environment. It's like the unitary version of the theorem. If it had a unitary version that we are using to get this condition, so these conditions ensure that after making these identifications, if I make these identifications in this equation, then whatever part I get written in terms of this I things, that will, if I throw out that part, the rest of the part will give me this unitary. And this is just SSK S phi r minus S phi l, there is no mixed terms and the couplings are real.
This action is real.
Yeah, real unitary. And couplings are real and there are no mixed terms of phi r, kind of phi r.
Mixed terms
Sorry?
apart from real terms, we are supposing mixed terms.
Yeah, because mixed terms, if you keep mixed terms, that is supposed to be non-unitary. That's what we discussed before there. In the influence functional only, when you have a non-unitary theory, then you have this influence functional, in which case you have mixed terms in that. If you don't have mixed terms, it will be unitary always. You will always be able to write it as some S phi r minus S phi l, in which case it remains unitary. For example, let me give just small list of trying to list down these conditions. It's going to get for say delta. You see that this is going to be phi, this is going to be phi. Imaginary coupling of L alpha, beta is imaginary of Z. Therefore, we will be able to make this identification that we will discuss. Other operators in intelligence were also discussed. Let's write down. This I go to this way, but actually this comes from 3 of such terms. The 2 terms will be and then also you get this magnitude of lambda. So these 3 terms will result in this thing. Okay, now let me discuss. Let us go to the perturbation theory. The upper branch is phi r, the lower branch is phi l. And if you have this kind of operator insertions, then you have a phi r phi l mixed term. And that will violate the inequality. I mean, if in the action you have that term, then it will violate the inequality. If in the action you don't have that term, then you can still deal with this kind of operation insertions, but they will not be mixed. I mean, the operator insertions always you can make that, then it will just be non-time ordered. Yeah, correlation function you can take any 2 correlation functions. But if you take the action to be mixed itself, if you remember the Schwinger-Keldysh formalism that we defined primarily, there was no mixed terms at all. That by itself there was 2 copies of this. One is this, one is this. We identified these 2 at whatever time we are interested in. Ideally, in its scattering process, we could identify this at plus infinity. Although we don't know about what is the outvacuum at plus infinity, by this identification, we can avoid talking about plus infinity type things. But we did not have this mixed terms anywhere in the description of Schwinger-Keldysh. We basically put it by hand to make it non-unitary so that we can handle situations where we are integrating out a part of the plane, and then we will in fact have an action where the mixed fields will be there. So that's how, if you remember, I discussed this Q and X degrees of freedom, and if I integrate out the X degrees of freedom, I will have Q action which will have purely Q parts, purely Q not Q prime parts. Q prime is the copy of Q, like phi a is a copy of phi r, and also mixed terms where Q and Q prime both will be used. So that was one way to see that if you, after integrating out in whatever you get in the influence function, you have mixed terms. for propagators, our propagators simply we already discussed before, just writing for completeness. For in propagators, which was written for dotted lines. For mixed propagators, which let me denote by some P and some M. Launching. Propagators with 2-point vortex. Written in this form. I mentioned this before that there can be, if there are vertices in the mixed thing, then there will be other things as well. Yeah. Basically, vertex I will include in this way. If there is no vertex, I will write it in this way. And the 2-point vortex will include a factor of minus n delta square. This vertex factor. And then other vertex factors where there are 5-4 kind of interactions going on. There can be many such diagrams. Possible diagrams are of this kind. Here I will associate this is just my usual side lambda. This comes from actually I have based the primary action that I wrote. But if you look at that action, you find that from there you can relate which will be the corresponding vortex factor associated with each of these diagrams. Minus lambda delta. So remember that in closed unitary Schwinger-Kelvin theory, which was the unitary action that we wrote down, in that case we have only this kind of propagators and not any mixed. Actually not only this, but this or this. This for phi r and this for phi l. There are mixed terms, then these propagators will also come in. So, what we would like to do is now compute corrections to vortices and propagators to study the renormalizability of the theory. No, unitary theory, this kind of propagators will also come. Only these two propagators. Because there is nothing like phi r going to phi l. Okay, let's say if I had this kind of propagator, either this or this, both cases can be possible. Let me study this. Possibilities of the corrections, one loop corrections, will be either this plus this plus a mixed one. Okay, and let me write this as this is a minus side lambda, of course, will write then AR, we write this now and write the size will be better. Then this will be lambda delta, and this will be again mixed. So, 3 of the things here, so I should get IC. And this AR, AL, and A. sum of all contributions, apart from also there is a let's say this cannot be the whole theory, of course there is a corresponding vertex. Minus IN square will be formed. If we evaluate these terms, which are supposed to be divergent, one finds out that the divergences are all divergent parts are all same. And now, further going on, I will probably not go through all such details. I will sort of write down the expressions that they, after the derivation that they get. Here, basically, in computing such divergent diagrams or divergences, you have to also get rid of the divergences by including local counter terms, and the integrations have to be done by something called Bhattacharya method, which is you can find these details in the appendix of Chandan's thesis and the Jana's thesis. And what you will get is after we do the integration, we will write this as for the general dimension, this is 2 minus 4, although we previously did this for d equals to 4, for t minus 3 dimension, this will be the expression. These things will all come into while you do the integration and introduce counter terms. For example, you will introduce an energy scale using which you will be able to compute something like a beta function as well. So we have this kind of expression, and from this now, when I talk about the counter terms, I'll have to introduce some delta n square like of things in the integration, which will be like vertex, where this will be delta n square vertex and so on. Sorry? Mu square 4 pi e power minus some gamma e here. These are just parameters which will come when you do the integrations. Mu square is the energy scale that we are going to be using. These are not going to be very important. Basically, what one can see is beta for n square, this coupling n square will come out to be basically g n square over d n mu is gamma 4 pi square. Similarly, one can also compute beta of delta n square, delta, and that comes out to be, in fact, what is the way? This basically tells us that when we change the energy scale while we are looking at the twin, how does the couplings change? Whether our perturbation theory is valid or not, and such things. Now, if you remember, this is again made of n square. When you remember that we had this Lindblad condition, which was imaginary of m square equals to m delta square. Now please assume that in my field level thing, the Lindblad conditions were satisfied. Then, and I want to check that basically whether the Lindblad conditions are satisfied in the one loop as well. What I can do is I can take a imaginary part of this equation, which will be imaginary m square, beta of imaginary m square, and I can take beta of m delta square. Then what can do something which is called Lindblad violating, the beta function for Lindblad violating couplings. Beta function for Lindblad violating couplings. If Lindblad condition is satisfied, then this coupling should not be there at all. If I compute this, what I will get is just using those two expressions. I get 2 of square imaginary of lambda coming from that lambda first line plus 4 imaginary of sigma minus 3 lambda into 2 of this one. And if you look at this expression, this part of the expression also was a third Lindblad condition that we had. So the beta function of my Lindblad violating coupling in the first order is proportional to another Lindblad condition in the tree level. So to be in the tree level, whatever in the right hand side is in the tree level. And since this we already we assume that in the unitary theory of the tree level it was the Lindblad conditions were satisfied, then it means that I can just say this coupling beta function for this Lindblad violating coupling is 0. If this Lindblad condition this is 0 at one loop, if this Lindblad condition is satisfied in level. Now one can similarly get beta functions from functions for quartic couplings. Where we have to basically we have to use certain 4-point functions, and there are only bubble diagrams come out contribute to the divergence. And these diagrams are the following form. I keep the side lines as solid lines, but in the middle part I can take many cases, like both of these lines to be solid, both of these lines to be dotted, one of the lines solid and one of the other lines dotted, and then the other way around. Then I can also take things like half of the line dotted and half of the line solid, then the line dotted or half of the line solid, half of the line dotted, one line also dotted. Such I will actually get 10 such diagrams out of this kind of combinations. And I can name them in following manner. So here both of these propagators are R propagators. So I will name it as BRR. This I will name as BLN. Both of these propagators are BLN. So this one, let's say I will call this as BRN. The lower one is R, and one is L. So in that way, this will be BLR and so on. There will also be things like this is, for example, BR P. So remember the P correlator was of this kind. But this will be something like BP or BME, something like that. In such correlators. And the form of them also I can write. Let's write down one or two of them. The Aryan will be something like this one. Of course, without including the external part here, but what I'm writing is for I'm writing with P. But if I want to be precise enough and I include this external momentum which are including, if it was say Q here, then another will be some Q coming from here. Then if I consider one to P, another integration I will have to take from P minus Q or something like that. That will come like that. But there are two propagators, for example, the RP is this one. And for the R thing, I can write this part. For the P thing, I can write basically P minus A. So, of course, I will use what I was saying Q here, Q in that diagram, that is actually K. K is the external momentum. So this guy. Similarly for RP, this part will be same. In the place of T, I will write down theta P0 minus T0 and the P minus T0. So it turns and get more such things written down. The K is the external momentum. In fact, one can show that if we choose one of them, we can write all other 9 integrals in terms of this function, as functions of this integral as well. So, for example, the Rn of A, we choose the Rp to that one function, and the Rn is the Rp minus A, and the Lp star. So you can compute each of them and make these values. And actually, if we introduce another integration, compute the full version of the RP, should be like d for P, d for Q, over to minus I will make this square plus c square minus epsilon so according to think of this as we indicating what the external momentum is. This comes out in the full form of the RP, and this is actually not very easy to evaluate because one cannot rotate this expansion since there is a pole in the real axis, and also there is a state function in the loop energy. So space and time are not in the equal footing. One has to, the basic way to solve this kind of equations is one has to primarily solve the time integration and then the space integrals. But let me write down the final answer of this Again, the computation of this is given in the appendix of Chandran Java thesis. We write the final expression. It is very similar to the beta function, or not beta function, but the A that I wrote previously for previous diagrams. I wrote this A case from which I derived the beta function for A square and so on. This in fact is just half of that. And so this is and in a unitary case only this BRR diagram would have been there, no mixed terms. Mixed term variables would have been there. But the corresponding beta function be able to, from this kind of diagrams, we will actually be able to get the beta function of lambda, beta function of sigma, and beta function of lambda delta. This is these three, once we derive, we can now again try to basically compute the one loop Lindblad condition violating coupling beta function, which will be this imaginary of beta lambda, imaginary of sigma minus sigma. Compute this completely and use these expressions to get this expression. And here again you can see the first part, we have something that is the Lindblad condition itself. So this part, this is basically this part will again be proportional to this thing. So if this was true in the tree level, then in the one loop again this beta function for Lindblad violating condition will be so the idea is that the Markovian, for all three we can show such things, and the conclusion that one gets from here is that the Markovian nature, or basically the Lindblad conditions ensure that there is the action that we are dealing with is of a Markovian kind of approximation is valid there, and Markovian nature of plane 5/4 plane is not described under renormalization. Now I mentioned that this integration is not easy to perform. One basically the way one goes about it is primarily work with different masses M1 and M2 for the two different things that we had here. And basically, so this one you can write as M1 square, then this will be M2 square, and then the final for different masses, the expression comes out to be of this kind. What happens is these terms in this kind of terms that I do, RP will probably be this and this kind. The R part is the solid line and the P will correspond to this kind of coordinates. So in such integrations, this particular term that appears here, D for D equals to 4, this term will have a non-local nature in it due to this keys. These keys were not present, would have not been present in this non-local fashion if it was not considering M1 equals to M1 not equals to M2. So if M1 equals to M2, then this kind of non-local divergence. Yeah. The propagating particles in the two branches of this Feynman diagram, I am considering different masses. Let's see what happens. Basically, one comes across such terms which are non-locally divergent in this open bottom field theory expressions. Remember that such terms should not appear, or those theta function kind of things will not appear if there was not a mixed correlate or mixed field. Only this kind of things will appear. In a mixed case, such non-local divergences appear which you cannot get rid of by adding a local counter term. To get rid of those, you have to add a non-local counter term, and this non-local divergences are kind of generic features of the open quantum field theories. So you always get for this mixed kind of correlators, which are fairly generic correlators. In any case of theories, we will have mixed fields, phi r and phi n, whenever we are dealing with open quantum field theories, and then we will get such non-local divergences. This is one distinguishing feature of open quantum field theories when you try to renormalize it and study all the diagrams and corresponding divergences. You always find this non-local divergences, and this actually happens to be the most salient feature of the open quantum field theory, because you remember the thing that we started from, this difference correlator. We expected that to be 0 for unitary theory and non-zero for non-unitary theory. But once you have, before taking this correlator and computing everything everywhere, you have to get rid of such non-local divergences. And whenever you do that, final phi d correlators, when you are computing it in a one loop diagram, not in field level but one loop, that also comes out to be proportional to some nuclear violating conditions. Basically, like something of that form, imaginary of lambda minus 4, imaginary of sigma plus minus 3, and it comes out to be proportional to this. And again, that is valid that if this was 2 and 3 level, then even the one loop phi d correlator will become 0. So, if the Lindblad conditions are satisfied always, then it appears that the difference correlators, it is not only 0 for unitary QFT, which we expected beforehand already by looking at the GRR, GRL equality, but it also holds true in case of non-unitary QFT. So the actual distinguishing feature or the generic feature to distinguish a non-unitary QFT from a unitary one is to whenever you encounter this non-local divergences. Okay, so if I just try to write down the and there is should say that there is not a very clear understanding of why these non-local divergences appear in a non-unitary QFT from a physical perspective, but one guess could be that I am integrating out when I am writing down this non-unitary action, fingerprint action. I have integrated out all the environmental fields, with which also the effect of interacting with that environment is also still somewhere in the non-unitary action. So those environmental fields which has left some signature inside the action, that non-local interaction part might be resulting in this non-local divergences. That is one naive way to think about it. So of course, what are the differences between a unitary and a non-unitary QFT? Here we have real couplings, we have imaginary couplings. No linear conditions. Since there was no linear operator only, of course here the linear conditions are there. That ensures that the evolution that we are going to study is going to be a Markovian evolution. Then here you can sort of, in the sense I am writing these trivial Feynman diagrams, is that I don't have any cut diagrams inside my Feynman graphs. Here we have to deal with this non-trivial cut diagrams. But if we look at this kind of difference operator, this will be 0 in unitary case also, and actually a more stronger thing is that this, if the correlation function or the correlation function you are considering all the operators are different kind of operators, it is not necessary to deal with only 2 point, but even the higher point functions will give you 0 unitary as well as in the non-unitary case, again under the condition that the linear conditions are satisfied. If you do away with the linear conditions, then of course you get this to be non-zero. But the perturbative treatment might break down. The perturbative treatment, if you remember in the deriving the GKSL equation also, we use the perturbative treatment in orders of dt and so on. So that perturbative treatment you can relate to the Feynman diagrammatic perturbative treatment here, and that breaking down of that is caused by the breaking down of this linear conditions over here. And if that breaks down, then this phi will be non-zero. But if this is satisfied, then the difference correlators even for non-unitary and QFT will come out to be 0. And here I always have local counter terms. You can have non-local counter terms in case of. This is the main distinguishing feature. Divergences and the generic nature. This is true. I described one example, but even the open Yukawa theory has been studied, and we are also going to find such non-local divergences. Finally, both of these theories are normalizing, of course. The way we discuss the beta functions and so on, one can describe. Now, another thing that I forgot mentioning is that since some of the couplings were interrelated through this, for example, imaginary of z is equals to z delta, imaginary of m square equals to m square delta. So some of the couplings are related. So ultimately, the number of beta functions you want to study will be the independent number of beta functions, that independent number of coupling parameters that we will get after using this Lindblad condition. So it will be less than the total number of actual couplings that you start with. So yeah, it is not really the fact that when we see this phi d becoming 0, it is still saying us, telling us that our theory is unitary. It is not that. It is just through the Lindblad condition, it is ensuring that the theory I started from in the tree level was unitary, and I am making perturbative treatment. In such a perturbative treatment under Lindblad condition, it will, the difference difference correlator will not show any non-zero value. But if you get rid of this, it will show. And so, for example, if we did not deal with the non-local counter terms and we kept the non-local divergences as they were, we just introduced local counter terms, then also we'll still have non-zero parts in this kind of correlator, which will in fact be divergent. Yeah. So that's all I wanted to say about the Markovian approximation. So again, this after, for example, in a time, in a quantum mechanical situation, you would think this as something like a time evolution where the system resets after every dt time or something like that was the Markovian approximation. But here it basically means that the perturbative treatment that we are doing, perturbative order by order Feynman description, that perturbative description breaks down if you are not dealing with, if you don't satisfy the Lindblad conditions. So yeah, this is sort of the end of the open quantum field theory part. So unless anyone has any questions, you can also write to me if you have any questions. But in the last lecture, I'll try to answer if there are any questions further on these things, or and if there are not, then I'll try to just mention a couple of maybe directions that we are following, that is in open quantum systems, and some problems that people are also working on in open quantum field theory with the path being, or the environment being a holographic environment. That is supposed to be the most natural environment where you can apply Lindblad conditions or the Markovian T approximations, because although the path and the system, the coupling between path and system is weak, but for a Markovian approximation, or for example the reservoir time scale to be far less than system's time scale, for the reservoir time scale to be far less than the system time scale, you want the reservoir to be a very thermal kind of system or a very strongly correlated system by itself, so that your environment is thermal enough and you can apply this in Markovian approximation.